Okay, I think I'm live. If you can all see my screen, see me and hear me, maybe raise your hand or say yes in Zoom if you know how to do that. Okay, thank you. All right, so as you can imagine, this is going to be a little bit of a different experience. It's definitely weird for me not to be able to see people and have that kind of interaction, but we'll see how it goes. We've got about, pretty close to the full class. I'll give people a minute or two and then begin. Okay, let's get started. All right, so since we don't have this face-to-face interaction, I think the way that I'll do this is I'll try to lecture. I'll keep the chat open for any questions that people have. But I'll try to lecture for about an hour. We'll do questions. Certainly ask questions during the lecture if needed, but it's very hard to, I can't see people, so it's sort of hard to get a read on whether people need to ask questions or not. So feel free to use the chat. I'll give a little lecture for an hour. We'll do questions and answer. We'll take a break. We'll do another hour, same thing. And then office hours will be right after this for those who need to ask more questions. But without further ado, let me just get started on the first lecture for the class. So this is COP-3402 system software. It's section 2. So hopefully you're in the right place. Today's lecture is going to be pretty light. We're just going to go over some introductory material, get you started with some of the tools that we're going to use for this class. Okay, so today we're going to go over the course mechanics, the syllabus. I'm going to talk to you a little bit about some of my goals for you in this class beyond what's on paper for the academic goals. And then we're going to set up some of the infrastructure we need for this class, the virtual machine. So one of the most important questions to answer for yourself is, why are you taking this class at all? Why take any class? For this particular class, there are some reasons that I think is really, really important for all students in computing to do. So there are 3 important reasons to take this class. 1, to know your tools. 2, to be a better programmer. And 3, just for your own intellectual curiosity. So what knowing your tools? if we look at all technical workers, they need to be experts at the tools that they use. So pilots spend hours and hours and hours in classrooms. Carpenters may even build and design their own tooling. So in order to be effective at computing and an effective programmer, it's really important to know your tools. And in this course, we're going to be studying system software, in particular, the compiler. And the compiler is one of the main tools that a programmer uses because that's how you express your computation. And so if you understand the inner workings of this tool, it can help you become a better programmer. And one of the reasons that doing this can make you a better programmer is that all programming languages have many things in common. And so learning how they're implemented gives you insight into how other languages work. So if you go to a new job and they have a new language you have to learn, a new programming environment, by studying the internals of these tools, you'll be better equipped to learn new programming environments. And lastly, compilers are just a fascinating topic, compilers and system software. They're my favorite topic in computer science. And I think they're really cool because they bridge both the theoretical side of computer science, all of the algorithms and theory and models of computation, and they bridge that with the lowest levels of computing. Right on top of hardware, you have to understand how the lowest levels of the system work in order to merge the high-level computer science concepts with how the program will actually run in the real world. And so we get a good smattering of different aspects of computer science in this course, all the way from systems up to theoretical computer science. A little bit about me. My name is Paul Gazzillo. I'm an assistant professor here at UCF. I've been here since 2018. And because I really enjoy compilers and programming languages so much, that is my research area. And some of my main interests is applying programming languages and program analysis to software engineering problems, as well as to some security problems. So if you're at all interested in research opportunities, this is my website. And if you click on research or even project openings, you can see some blurbs about each of the projects that I'm working on. And all of them revolve around doing some sort of program analysis, software engineering, some security applications. Okay. So let's first talk about compilers and why compiler writing is so hard to do, and why we study this in school, and what makes it so interesting and so useful to you as a programmer. Let's see if I can get this thing to work properly. Okay, this is a little askew. Let me restart this. Okay, here's my whiteboard. There goes my whiteboard. Wow, already technical difficulties. Okay, so let me give you an overview of what the compiler looks like from the 10,000-foot view. And we're going to be focusing a lot on the compiler this semester. So let's take a look at what the compiler does. The compiler takes your program, like file.c, as input, and produces, as hopefully all of you know by now, produces some executable. And that executable, the program you wrote, has some input and some output. And as you probably also know from programming, getting the input and output to be what the output to be what you expect for the input is really, really hard to do. So programming is hard enough in this model. When you have your compiler, it makes this task of generating machine code much, much easier. But if we look at the compiler itself is just another piece of software. And as another piece of software, it has its own source code, say in compiler.c, which you also pass to some compiler in order to generate the compiler. So this is called the bootstrapping problem in compilers, that if you want to compile a C compiler written in C, you have to already have a C compiler. So the way to solve this is we write the compiler in machine code first, but we're not going to do that. We're going to use a compiler. We're going to program our compiler in C, which is much easier. But this notion that the compiler itself has to be compiled makes writing compilers kind of tricky to think about. So one way to look at it that's a little bit simpler is that we're going to write a compiler in this class for a language called Simple C. So you'll have a program called Simple C. You'll pass it to your C compiler, and that will give you your Simple C compiler. And from the view of any other programming task that you normally do, the input and output of this program that you'll write in this class just happens to be source code, and the output happens to be machine code. So as long as you can keep track of what's the language that you're writing the compiler in C, what's the language that you're compiling, Simple C, and what's the language that you're generating, assembly, as long as you can keep those three pieces separate and straight in your head, writing compilers is really not so bad and can actually be really fun because you're automatically generating code that runs on a machine. Okay, so that's compiler writing from 10,000 feet and the bootstrapping problem. I may need that later. So the bootstrapping problem is we can't write a C compiler in C without having a C compiler already. And so the way it's solved is you write the machine code first, and then you can actually compile the compiler in the language that the compiler supports. All right. The syllabus and course information is publicly available on the web at this site. Let me go over the syllabus and the mechanics of this course, take any feedback on what you might like or dislike, or what problems you see, if any, with the syllabus. So firstly, the technical details. This is section 2. There was originally only one section of this course, but it filled up quite a bit. So they opened up a new section, which I'm teaching. I'm your instructor, Paul Gazzillo. We have 2 TAs. One is Josh Santana, who you'll see later today in lab. And the other, I have not updated the webpage yet. She hasn't been hired yet, but Kai Garcia is going to be also TAing. These are the proposed office hours, and I took a poll. I had an announcement where I took a poll to see if my office hours at least were okay with you. If you can't attend any of these, feel free to send me an email and let me know. It's very hard to schedule to make sure everyone can have access to office hours, but I want to make sure everyone can come to at least one of these sessions, ideally one with me if you prefer coming to office hours with me. So hopefully, as you know, because you're here already, the lectures are Friday at 10 a.m. to 12:50. Because it's a double lecture, I'll try to make a break in the center of it. I don't think I'm going to be lecturing for 3 hours. That's going to be a little rough. We'll probably have 2 one-hour lectures around that with a break and time for questions and answers. And if we end early, we can just start office hours early because office hours will be directly after this. These are your labs. Labs are no longer BlendFlex. BlendFlex is a little complicated. I'm still not entirely sure what it is, but labs are just going to be virtual now using the same Zoom chat that we're using for lectures. Feel free to attend whichever one is useful to you. The material should be the same. Okay, also on this syllabus will be the schedule of lectures. And I will try before each class, I will update the lecture notes for the class. So each one of these lectures will have a link that shows you the lecture notes. And these are basically the slides that I'll show during class with some of my speaking notes grayed out. And so that way you'll be able to review, you'll be able to review the recording of the lecture. You'll be able to review the lecture notes. There'll be instructions in there. This class will be broken into 3 main sections. For the first 4 weeks, we'll go over introductory material. I'll get you set up with all of the tooling you'll need for this course. So as I'll talk about in a little bit, part of this course and part of my objectives in this course is to get you proficient at programming tools, in particular the command line. So it isn't just, so it's actually part of the course. I'm going to give a little more lecturing on how to use the command line, and hopefully everyone will get some good muscle memory in this class and be able to be really efficient at the command line and look like some elite hacker when they're coding. So we'll go over some of those system tools. We'll program together in class a toy compiler that you can follow along and compile with. Then we'll go over the main project for the semester, which is implementing Simple C. So that's the introductory material. For the next part of the class, we'll go over the front end of the compiler, and that's the part that processes the source language for the compiler. And in there's a whole lot of rich theory, computer science theory that goes into this that can actually be put into practice to do analysis of languages. And for the last major part of the class, we'll talk about the compiler backend. The compiler backend is what generates machine code. And there's a whole lot of interesting systems knowledge in the backend, because in order to get your program to actually run on an operating system and a piece of hardware, you have to interoperate with the existing software and how the actual machine ISA, instruction set architecture, works. So these 2 parts really show how the compiler bridges this formal computer science theory with how the actual physical machine and systems work. And hopefully, if we have time, we'll cover some special topics that are very interesting to me, at least, just program analysis, automatically figuring out what code does without having to run it, and some security applications of programming languages. And then we'll review for the final. All right, so here are all the assignments that we have in this class. For a little terminology, I call assignments any grading activity that you do. And I break those assignments into 3 different categories. One is just logistics. And these are, you get points for these, but they're kind of ungraded. They're just to make sure that you're actually using the tooling that we need in this class to do the project. The first thing is the Git Classroom Signup, and we use this to grade your project. So submitting code is through Git. This has 2 main benefits. One is it makes it easy for us to automate grading, but it also makes sure that you learn version control. This is something that students in the past have been very happy with, because when they go to internships or jobs, version control is just standard in the industry. So having some experience with it, and I'm going to force you to use it on the command line. Well, I'm going to ask you to use it on the command line, and then you'll really know the nitty-gritty nuts and bolts of how version control works. The second one is virtual machine setup, which we'll go over today, setting that up. And then some kind of loosey-goosey participation in course engagement. So don't worry about this too much. I'm not taking attendance or anything. As long as you're following along with the course and doing the homeworks, this shouldn't be any issue. But this gives me a little discretion in the grading, you could say. In the homework category, these are things that you submit. If it's code, the toy compiler is submit through GitHub. If it's written, the regular expressions and grammars, it's submitted via web courses. And these are really more for making sure you're following along in the course. They're graded, but the effort is taken into account in grading for these. And the main part of the assignments for the class are the programming projects. And there's 4 of these. These are pretty substantial. They're not something that you could just start the night before. I strongly recommend not waiting until the end of the semester and just trying to do all of it. It's virtually impossible to do. Ask your colleagues who have taken this course or taken my course. It's a substantial project. So it takes time to do, but hopefully my goal is to give you the tools necessary so this won't be so hard to do, but it does take time to write a compiler. So the goal in this class is to make a complete compiler by the end of the course that you can actually use to create GNU Linux programs that can fit into the programming environment, your Linux programming environment. Let's see, I'm seeing some questions on the chat. So let me answer some of these questions before I move on. So scripting language, there's no particular scripting language. There will be some automated scripts to help do grading, and those will be in whatever the TA wants to write it in. So you can certainly use Bash. We're going to be on a GNU Linux system. So you can use whatever tooling is available there. Bash is the default command line prompt there. There will be lab today. The lab instructor will go over installing the virtual machine and helping you with GitHub. Thank you for implementing version control in the class. Great. It's also useful for us. GitHub is, I mean, it's commercial, a commercial company for using Git, but they provide this classrooms environment that makes it convenient for downloading your, maintaining repositories, creating them and allowing us to download them. But Git, you don't have to use GitHub for Git. GitHub is not Git. Git is a open source, free and open source version control software, decentralized, that you can use anywhere you like. Labs will be recorded as well. Okay, let's go over everyone's favorite part of school, grading. That was sarcasm. All right, so to make things simple, 1 point on activities is 1% of your whole grade. I've broken down these assignment percentages, so it's very easy to see. If you get 1% off on a programming project, that's 1% of your grade. These are in the 3 categories for assignments. So logistics, 1% for setting up classrooms, 1% for the virtual machine setup. Git is, I mean, these are really for academic activity. So if you have a financial aid or a scholarship, please do this homework. It's not real homework. You just plug in the URL for your repository. Do that today because it's due tonight. 3% for this participation and course engagement, kind of instructor discretion thing. Should be no problem. There's no attendance being taken, but as long as you're following along in the course, shouldn't be a problem. Homework assignments are 20%, 10% for your own follow-along implementation of a toy compiler, 5% each for some written homework. And as I mentioned before, for grading these, we take into account effort. So it's okay to try and fail or make mistakes. But if we see that you're, submitting something blank, obviously we're gonna not give that any points. But this is really to make sure that you're following along in the course and you're prepared for the final as well, because we're going to be using these homeworks for the final projects, for the final exam as well. Okay, so the majority of this course, 60%, is the programming projects, because I really, really want to get you building a big piece of software, something that is larger than many of you may have implemented before. And I find the programming part really, really important. So each of these programming projects is 15% each. To avoid any kind of subjectivity in this grading, we're going to be grading via test suite. So we'll give you the test suite, we'll give you a bunch of tests that you can try yourself, and we'll hold a few tests, some secret test cases that will apply when you're grading your repository. So you'll have a large test suite that you can try out and see what your grade might be before you submit the project. And there's a little bonus here if you can get the entire compiler project working correctly for complete programs. It's a big challenge, but if you can do it, it's a very satisfying challenge. Programming projects are all individual. All the homework is individual here in this class. So no group projects for the compiler. All right, and then there'll be a final. That's only 15%, and that'll just be a combination of lectures, homework, and projects. Have not actually looked into how the final is administered remotely. I know there are some pieces of software out there with, and there are lots of views from students about some of this software. Some of it does seem to be kind of spyware, but I don't know. Well, I'll have to see how that goes. We'll have to see how we do the final. I think Web Courses has support for this as well. Okay, so the late policy for homeworks and projects. So, there's 3 categories of assignments: homeworks, projects, programming projects. Logistics. So homeworks and projects are considered late after 11:59 on their due date. The due date for all of these is a Friday. As long as I didn't mess something up, they should all be on a Friday. And the due date will be Friday night. For homework assignments, the written stuff, the toy compiler and the 2 papers, those can be turned in up to 2 weeks late. My intention is that you kind of follow along in the course and do these as soon as possible and not make them late. So they have a pretty stiff late penalty, but also keep in mind they're graded for effort as well as correctness. So that's much less harm to submit these, even if you're not 100% certain about the answers. The programming projects, however, can be turned in or resubmitted after their deadline anytime until December 11th, which is the day of our final. And each of these, for each of them, if you turn them in late, you get a loss of 2% on your total grade. So 2 points out of 15 are lost for turning them in late. So it's a very lenient late penalty because I'd like you to try to get the compiler done. So you can turn it in. If you don't get many points when you first turn it in, or it's not working correctly, you can retry and resubmit. And we won't regrade instantly, but you can continue trying until the end of the semester to get all of the projects written. Now, one thing that's a little tricky about this project is even though it's 4 individual submissions, it's one giant compiler project. And doing, say, project 2 requires getting project 1 right. So in order to not penalize you for the entire semester for messing up on project 1, I'll give you some binary version of the compiler that we wrote to, so that you can work on project 2 without having to have finished project 1. And if you have time to go back and work on project 1 and resubmit, that's okay to do. So lenient late policy because for projects, because I really want you to try to successfully get this large project implemented. It's probably going to be one of the larger, at least more complicated projects you'll write, almost certainly in college, and maybe even after college. It's a complicated piece of software, but you can definitely do it. It's definitely achievable. You can ask other students who've taken my class before. You can definitely do it. All right, let's look at questions here. Is this class hard? Yeah, I mean, it's challenging. It's challenging. I don't know if it's really worth it to take a class that doesn't challenge you. And if it's easy to do, I mean, yeah, I guess you can get the grade. But one of the reasons that I structure the late policy and grading like this is that so you have an opportunity, at least for the whole semester. You know, I don't have control over the entire curriculum for the college, but I do have control over the curriculum for this course. And I'd like you to take the, you know, the whole semester to give yourself time to Oof. Yeah, I don't know. I breathed in something. Of course, day one. Yeah, I know. Seriously. Well, as long as I can't catch corona from Zoom, which I guess you never know. Okay, I don't remember what I was saying, but yeah, for the whole semester, you have the whole semester to do this project. It's a big project. You can do it. Take the deadlines as real deadlines, but just realize that if you make a mistake, keep trying. Writing good code is really about making incremental progress and gradually improving your code. If you have this attitude, which I certainly had when I was younger, of I write code once and I never revisit it again because it just works, that's not going to work on a project as complicated as a compiler. And it's just kind of bad practice when you're trying to write reliable and good code. Hacking together code has its place for sure, but for making production quality and professional software, it's not a great approach. All right. Yeah, I have water here. Okay. Let me finish up with this, with the syllabus. Okay, so course info. So you can read over this yourself. My goal, I tried to make my goals clear already. I'll talk a little bit more about my goals in this class. I certainly want you to learn about compilers, assemblers, linkers, and loaders. But my view is that learning this stuff is not just, I mean, I find it interesting on its own, but learning this stuff is really useful for anyone who wants to do anything in computing, because understanding your tools is just critical for any technical field. And I'm also hoping that I'll make you better programmers, because working on large software really exposes you to the reasons why we have computer science, why you have to do, say, object orientation, or why you should have formal notions of algorithms. When you have to do really, really large critical software, all of these tools become really evident why they should be used. So for course materials, there's no required textbook, but the classic Dragon book, which is this one here, Compilers, Principles, Tools, Techniques, and Tools. The Dragon book because it famously has a dragon on the cover. This is the recommended text. I'll give readings for some classes in this text. So if you do have it, or you like the more formal side, this is a good resource to have. I strongly recommend this book just in general. This is not a textbook. This is like a guide by Brian Kernighan, Rob Pike, some of the original Unix guys from AT&T. And this is a fantastic book on the practice of programming, on good software engineering practices. It's an excellent book. I'd highly recommend it. And if you're really, really interested in compilers like I am, these are all excellent textbooks on it. Advanced Compiler Design and Implementation. This is extremely good if you actually want to write a compiler that's really high performance, has lots and lots of algorithms and detailed designs. This is a classic academic textbook by Andrew Appel. It's a little less formal than the one I'm recommending for this class, and can help you actually build a compiler. And there's some other textbooks here. All right, let me check questions. Do students sometimes find that they have to change previous portions they submitted to get later assignments finished? Well, I'll give you the previous assignments as a binary object file, so you can just link it in with your own project. And if none of those terms make sense to you, next week we're going to go over how separate compilation and linking and loading work. But no, I'll give you a compiled version of project 1, 2, and 3 so that you don't have to worry about getting the earlier projects right in order to successfully accomplish and finish later projects. And you can certainly retry and resubmit. So just keep in mind, you know, if you got 13 points on project 1 and then you submit it late, you're going to get 2 points off anyway. So it may not be worth it. Let's see. Okay. I don't think there's any other questions that I need to answer here. Oh, is the textbook required? So it's not required. We should have enough resources in class with the lecture notes and being able to rewatch the lectures. I hope that this should be enough. A lot of what the textbook gives you, it's fairly formal and algorithmic. So I think hopefully through the materials I give you and the websites I give you, because I'm going to use slides from other courses and websites from other courses, should be enough to do that. I think the dragon, so somebody asked why are there dragons on so many compiler textbooks? I guess the dragon is like the compiler. It's a really difficult challenge. And so writing the compiler is slaying the dragon. Compilers are beasts. Yeah, that's another example. That's another good way to look at it. That's my guess. I don't actually know. Okay, so really important part of the syllabus. Some of this is boilerplate, but it is really important to keep in mind. For this class, as someone asked and I mentioned, all work is individual in this class. And so here's some nice scary text on not getting unauthorized assistance. So keep in mind the UCF's golden rule, and really in my class, my goal is to have all of you get A's. I'd be totally fine with that if you can all achieve what I'm putting out here. It's a challenging course, but my goal is to get you really improved at programming and understanding these things in computing. That's why the late policy is very lenient, but keep in mind it's a kind of a double-edged sword. If you wait till the last minute, there's no way you're going to be able to finish these projects just waiting till the end of the semester. But I also want to make sure that you realize that it's okay to fail a little bit on the projects and get them wrong, as long as you go back and retry and improve things incrementally, make them work better, and eventually you can get it. So just read over this. These are all the boilerplate text about academic integrity. There's a nice new section here on statement regarding COVID-19, which is now required for syllabi. This, I guess, doesn't apply to us. We're no longer BlendFlex. We're all virtual. So I don't think you have to wear face coverings because we're not on campus. I notified you about the change in course modality from BlendFlex to virtual for the labs. And you can read over the rest of this. All right, other questions on the syllabus? Any comments, issues, concerns? Do things look wrong? Did I miss something? So somebody asks, we specify Virtualbox. I don't know. I think the tooling, so somebody asked if they can use Vmware instead of Virtualbox. I think the tooling I use does support Vmware, but I have never tried it. And we're going to sort of officially be supporting Virtualbox and Vagrant. But if you can get it to work yourself and it works fine, then also another thing with using VMware, yeah, I think it's probably fine, but I don't know. It's probably fine. If you can get it to work, then I'm sure it's fine. All right, any other issues, questions, concerns on the syllabus? Oh, how important is the CDA class? That's a really good question. So this version of system software, so I tend to change it every semester. It's a kind of a lot of work. Maybe I'll stop doing that in a year or two, but I'm changing up the course regularly. And for this version of the course, we're going to be generating Intel assembly, the actual machine code that runs on your bare metal hardware. And so for this class, having a good background in how an ISA works, how an instruction set architecture works, how the machine actually works, will be useful. We're not going to be using MIPS, which I think is what's used in CVA, but we are going to be kind of doing a lot of low-level stuff with assembly. Oh, somebody said, "Oh no," but don't worry, it's not so bad. Remember, we're generating it. We're not writing it by hand. I don't know. I mean, for some people, this is really fun to work with the low level and work with assembly. We're going to see how the actual system works from the like nuts and bolts level. So some people like it. Somebody asked, do we get a generate button, or is it more involved than that? You're going to be writing the generate button. You're going to be making a generate button that when you press it, it's going to spit out assembly. That's what a compiler does. We'll look more closely at the language we're going to be compiling, but it's basically going to be a simpler subset of C. Okay, some interesting comments here. So don't worry about it. We have an entire semester to go through in detail and very slowly and carefully all the aspects of doing this. All right, let's see. So that's the syllabus. Any other questions on the syllabus? Let me see what else I have.
Actually, I do have one quick question, if that's okay.
Oh, yeah. So I do want to also point out that we're recording these, and they may be publicly available at some point. So if you don't want your voice or picture on them, then use text. But voice is totally fine too. What's up?
But yeah, actually, I was just about to ask about that because I might have some times where I have to step out to help my niece with something because I'm kind of babysitting while doing class. So I just wanted to make sure that we'd have notes on the side outside of.
Yes.
Like,
so notes will be available on the website if you go to lectures, and each day will have have the lecture notes from each day. So these are basically the slides with extra notes interspersed in them. And the lectures will also be recorded. Okay. And I'm using this, Zoom cloud recording. So hopefully that's working. Let me make sure this is actually recording. Yeah, it's recording. Yeah, so they'll be recorded and you'll have notes. So my hope is that everyone will attend live. But even before COVID, I was recording my courses and putting them on like YouTube. Just because I know it's helpful to go back and, sitting in class and trying to stay focused for 2 hours and catch everything is not so easy to do. And in this age of technology, it's very easy to record these broadcasts. I have no idea who even asked that question. That was just a disembodied voice. Where does this show up?
Thank you, by the way.
Oh, no problem. Yeah, okay. Well, yeah, don't say your name. Yeah, so they are all recorded, and these may be released publicly at some point. So if you don't feel comfortable having your voice or your video publicly displayed, I won't just, the chat is not displayed. Released publicly, probably on YouTube, but I haven't decided whether to do that yet. In the past, I've released the lectures on YouTube. For somebody asked about scheduled lab times. Really, in principle, no. You can go to either. I don't see a problem with going to either lab time. Okay, so if there's no other questions on the syllabus, we still have time. So I'll probably stop around 11. We'll take a little break, do some more questions if you have them. We'll take a break, and then we'll do the next half of the lecture. All right. For this class, as I've kind of hinted at, is I have a little secret objective to this class. So don't tell anybody, but my secret objective to this class is not just to teach you the nominal content of this course, system software, but my objective is to make you be a better programmer, to train you to be better at the practice of programming. And I think compilers writing is an excellent way to do this. It's made me a better programmer and helped me get good jobs and internships because of the work I did on just building a compiler in class. So in my humble opinion, from the technical side, I think great programmers have three things that they're really good at. That if you look at all of them, they all are able to do these three things really, really well. So this is not the soft skill side or the management or team building side, just from the technical side. And these three things are knowledge of the programming language, knowledge of their programming environment, and perhaps surprisingly, some knowledge of computational theory, some of the theory side. So a lot of practicing programmers may kind of dismiss theory and say, well, you don't need a degree to be a good programmer, which isn't true in some sense, but having some computational theory is actually, perhaps surprisingly, extremely useful for programming. Here's why I think this is the case. So knowing the language should be pretty obvious. You can't actually program without some language, even if it's machine code or assembly language. But really good programmers not only can use the language, but they know how the language works in detail. They know how the actual language constructs in detail. So a good programmer can sit down with a piece of code, even code that they haven't written, look at it and actually think about its execution line by line. And having this level of detailed knowledge about your language is incredibly useful for programming. If you've got to do debugging or you have to extend some piece of software, this is really very, very hard to do without having a detailed understanding of the programming language. And compilers is an excellent way to learn any programming language because the compiler, for the compiled languages at least, implements how the language itself actually works. The compiler is the implementation of the language. So if you understand the details in the background behind how this language works, it will help you understand and program the language a lot better. Now, C is a language that I'm sure you all struggled with and have been confused by at many points, myself included. And one of the reasons is that C, from a compiler perspective, C is a fairly simple language. But simple does not necessarily mean easy. It's deceptively simple because even though the language itself is simple, there's very few constructs. There's very few things that you can write in the language, very few constructs you can use. It's very hard, that makes it very hard to use. If you want to do something simple like make a data structure, it's complicated to do this and complicated to get it right. And we'll, by looking at the compiler and how compilers work and how programming languages are implemented, we'll get a little more insight into why that's the case. Knowing your programming environment. This, I think, is really, really important and kind of underrated, particularly in academia. It's very easy to go through a computer science program and learn very little about the actual tools you use for doing software operations. And in these days, where software operations like DevOps, continuous integration, all of these techniques, version control, these are now standard practice. I think it's pretty tough to go somewhere and hack something together on Notepad, copy it to some remote drive. Hopefully people don't do that anymore. Software operations has become its own entity in its own right. So the programming environment includes the editors that you use, the IDEs, version control, all of the system software, libraries, linkers and loaders, the operating system. And these are critical for a programmer because this is how your program actually runs. So if you really understand the language really well and you can write code really well, if you can't turn that into a runnable binary, a runnable piece of software that is integrated with the rest of your operating system, then there's no computing. There's no physical computer that's actually operating using that program. And we're going to go through in this class in some detail through a whole bunch of programming environment tools. We're going to be using the GNU Linux environment. It's free and open source. I choose this because I use it in my own work. It's free and open source. It's not tied to any particular proprietary company. And because it's kind of the classic programming environment, it has influenced a lot of the modern day software. So if you can understand on the command line how to use these tools, it'll make the high level graphical versions of these that much easier to use. Being fluid at these tools helps you become faster and work with larger and larger software. If you know how to do separate compilation and break your program down into little pieces, you can write code faster. You can use debugging tools more easily. So using graphical interfaces is nice for ease of use, but it obscures a lot of the ways that these tools actually work. So I have nothing against GUIs. I tend to use the command line most of the time. I have nothing against using graphical interfaces. They're really good for speed and ease of use, but they don't substitute knowledge for how these tools actually work. And compilers are a really, really good way to learn about this, because not only do you have to build a big piece of software using these system tools, the compiler has to integrate with the programming environment in order for it to run. So in order for the compiler that we're going to write in this class to compile and work on a GNU Linux operating system, we need to know how those libraries work, how we integrate with them, how the operating system handles linking and loading. We need to do that. All right, and so this one is maybe not in academia, it's not controversial, but for practicing programmers, this may be controversial. And you can probably look at all sorts of flame wars on Reddit and news groups, if people use those anymore, about whether you actually need formal education in computer science. So my view is that while programmers certainly, you don't have to go to college to learn programming. It's a skill that you can practice and learn on your own. Even those who don't use formal academic models always use some kind of mental models of computation. Good programmers do this. Good programmers have some mental model of the machine and the programming language. And even if it's not something from a textbook, it's something that's going to be either they developed on their own or something that they read in a language manual. So if we look at C, for instance, C has a mental model of the machine. It treats the machine as basically a giant piece of RAM where each variable is some reference into that RAM. And the addresses of the RAM is exposed to you. So not only can variables point to data, but variables can contain addresses to other variables or other data in memory. So that is a kind of mental model of the machine. The physical machine may not exactly work like that. It's not the only way that you have to reason about computation. You can think about algorithms without thinking about pointers. But C is useful because it's very close to how the actual physical architecture works. Its mental model is very close to it. But it's not the only way to think about computing. It's certainly useful for systems implementation because it's so close to the actual physical hardware. But there are lots of problems, algorithmic problems, that are not so easy to think about in that mental model. So does anyone dislike recursion or been confused by recursion? Has anyone, or does everyone just sort of get recursion? Yeah, I've been confused by recursion. So I think probably everyone has at some point. And let's see if there's people are saying yes. So people prefer iteration. It's definitely a confusing thing. Now, I think part of the reason for this is that the mental model that C gives you of the machine is not really amenable to recursion. And as we'll see when we actually implement a language that supports recursion, the machine itself, strictly speaking, does not use recursion as its model. The machine is just, as you saw in CDA, just a sequence of instructions with branching. And recursion actually is not really supported on the physical machine. We could probably have a debate about this, but strictly speaking, there's no support for recursion when it comes to the physical machine. The compiler actually generates special code that simulates recursion on a device that just has a flat piece of RAM with branching. So in some sense, the physical machine doesn't really support recursion, and languages that support recursion have to actually translate it to machine code and add extra special instructions that emulate recursive functions. So my kind of theory here is that trying to learn about recursion and in C makes it really, really hard to do. But if we abstract away from, or move away from C's mental model and think about a mental model of recursion. And there are languages that actually make this kind of recursion easier to reason about. It can actually be really easy to use recursion, or at least a lot easier to use recursion. For example, languages. Yeah, some functional languages do this. They make it a little easier just to kind of specify recursion. You don't have mutable variables or pointers. You can't change the values of variables. You can't you can't actually operate on the pointers. And when you specify recursion, you can use pattern matching to specify. Like if you're looping over or you're iterating over a list, you can do pattern matching on here's what happens when I've got just a list with no, that's at the end of the list, and here's what happens when I have a list that has more elements. So yeah, there's some languages that allow you to do this, like Haskell, Scala. Take programming languages here, and they'll show you more about different languages. But I'm more concerned with the mental model of recursion. And so if we move away from this notion of having to do bit manipulation and pointer manipulation in order to do recursion, that makes it kind of hard to think about. And also recursion, in my opinion, is much easier to reason about when we just think of recursion as a tree. So I don't know about you, but for me, I can think of trees. I can sort of write down and draw and picture trees. And if you can do that, and you can think about a tree traversal, then you can understand like pretty much any recursion if you do that, for the most part. You can understand recursion. Compilers is really good for this because one of the core data structures in a compiler is a tree, a syntax tree of the input language. And we're going to get lots and lots of practice traversing over this tree. But if you just remember binary tree traversal, pre-order and post-order, if you can do that, then you can basically understand recursion, all recursion. So yeah, most recursion can really kind of be boiled down into binary, pre-order and post-order. I'm maybe exaggerating a little bit, oversimplifying, but if you can imagine the tree, that's recursion. Okay, so that's sort of my view about what makes you a great programmer and how learning compilers is really going to help you with that. So to finish up this half of the lecture, here's someone else's view on what makes a great programmer. Larry Wall, one of the original authors of the Perl programming language, which these days you may or may not actually have heard of anymore. But here's his view of the three virtues of a great programmer. So they're laziness, impatience, and hubris. Maybe some things you never really thought of. So laziness here is not like, I don't feel like doing that task, so I'm just not going to do it. This is not the kind of laziness they're talking about. This is a kind of constructive laziness. So Larry Wall says, the quality that makes you go to great effort to reduce overall energy expenditure. So rather than saying, I'm just not going to do that at all, it's, this is taking a really long time. How can I automate it? How can I use a little bit of forethought and sit down and work out a problem so that it saves me time in the future? So as he says, it makes you write labor-saving programs that others will find useful and document what you wrote. So this is another point that I'll talk about in the second half. It's very tempting when you're given kind of small programming exercises to hack them out as quickly as possible. But it turns out in the long run, if you're making large software that you have to go back and other people use and you have to go back and revise, that strategy is actually increases your overall energy expenditure. All right, impatience is the next thing. Impatience is a good one because it sort of plays into this laziness. So one thing that's great about programming is this kind of instant gratification. You write code and you see whether you got it right and whether it runs virtually immediately. And so if you see that your code is just running slow, then you're going to sit down and spend time to make that computer work the way you want and work better the way you want. And one of the reasons that I want to introduce you to this GNU Linux operating system and this free and open source software is that you have a huge amount of flexibility, not just to use the software, but to modify it as you see fit. The last one that Larry Wall looks at is hubris, the quality that makes you write and maintain programs that other people won't want to say bad about. This is kind of an interesting one. So this is about taking some amount of pride and believing that you can write this really, really hard software. So one of the, my secret objective here is to make you a better programmer. One of the little secrets here is that for large, high quality software, no programmer is holding that whole program in their head. They're not able to reason about the whole program. One of the ways one of the tricks to writing good high quality software is to break it down into little pieces and get those really, really right. And so even if, like me, I can't remember what I wrote a week ago programming because I'm doing so much work and I have so many things I have to focus on. So making my code really documented and really clean and easy to read is not just some classroom exercise. It actually is useful for me in practice. All right, so that's the 3 virtues. Somebody posted an XKCD link here. I should probably not just click random links and have them open up here. Let's see. So we'll end this half of the class with this. Let's see. I spent a lot of time on this task. I should write a program automating it. Okay. So work on original task, automation takes over. Yeah, okay. So this is saying that if you always try to spend time on automation, you'll probably spend time on you'll go off on some tangent trying to automate that. That's pretty funny. So this requires this is why I'm saying that you don't always have to make the cleanest, most automated code. There are cases where just hacking something together is totally appropriate. It's really about the problem you're tackling. And up till now, you may have only been doing 50 or 100 or 200 line programs where it's very hard to see the point in doing extensive documentation and object orientation. But in this class, we're going to be doing a large, complex piece of software. And also, we're not going to be creating the automation ourselves. We're going to be using theory that people have developed over decades to implement our compiler. But this is very funny. XKCD has lots of classic stuff. If you're not aware of it, as a computer person, it's sort of de rigueur in the computing world. Okay, so, one question. Will this project be portfolio worthy? Unfortunately, you cannot share this code because it's a classroom exercise. But I would say that, writing the same piece of code that everyone else wrote hundreds and hundreds. I would say that classroom projects, unless it's like senior design where you're doing your own project, a classroom exercise is not a super convincing piece in your portfolio, from my opinion. If you really want to build a portfolio, join an open source project. There are so many projects out there that are willing to take basically free labor and with varying degrees of communities that are willing to take you in and help you out. So even just in, say, like the Linux kernel, you can go in and do some small plumbing or maintenance tasks, and you'll have your code included. And I think that, from a hiring point of view, that is way more interesting than here's a project that thousands of people also wrote, rather than I have some real world programming experience. This project is going to be maybe a little too real world for some people. It's going to be pretty intense, but it is also greatly simplified for class. It's supposed to fit in a few months, and hundreds or thousands of people are going to do it. Okay, so let's do questions for like 10, 15 minutes. Once that's over, we'll take like a 10-minute break. So let's see. So put all your questions in the chat. I guess there's not too many questions, so let's take a 15-minute break. So how does is 11:30 too late, or should we sort of start this up again earlier? How much time do you guys want to take for a break? Should we just do 15 minutes? 11:20? Let's do 15 minutes. Let's do 15. All right, let's do. I got to figure out how to do a poll here. All right, let's do a 15-minute break. So we'll reconvene at 11:20. If you want to stay, I'll answer questions here to stay. All right, so 15 minutes. We'll start again at 11:20. All right, is it okay to use the pre-existing GitHub account? Yes, it's okay. So as long as you go to that link that I give you on the GitHub Classrooms link, then it will create a private repository in my class organization. And as long as you do that correctly, it won't be on your own personal organization, and you can totally use your own project. 50-minute paid break. Are you offering a sponsorship? Oh, good. Oh, yes. Somebody said this before. All right. There's a question on using Windows subsystem for Linux. Windows subsystem for Linux, I've seen students use it in the past, even when I've provided virtual machine. And we're going to use a similar environment. I think Windows subsystem for Linux is on an older version of this Linux distribution, Ubuntu 18, I think. And it shouldn't be, oh, it was just updated. Was it updated to Ubuntu 20? Really recently. Well, at any rate, even when the GNU Linux distribution is the same, I've seen weird issues with it. Maybe this is a little anecdotal and mythical, but there was somebody who got like a null pointer error, and when they used like a debugger, it was showing up in a different place than it actually was in the source code. Or maybe it was something with debugging symbols. I don't know. Oh, okay. So somebody's asking. So for Windows subsystem for Linux, I don't know the difference between WSL1 and WSL2. I think VirtualBox also requires Hyper-V capability. Oh, okay. Oh, that's a little annoying that they lock Hyper-V. So if you use VirtualBox and Vagrant, they're just going to use the hypervisor stuff on your machine. Some students who have older laptops and don't have VTX extensions, the virtualization extensions in Intel, may have problems. Oh, okay. Yeah, I don't want you to use Windows subsystem for Linux. If you really, really want to use that, let's make sure that it actually works. But yeah, I'll go over in the second half the virtual machine we're going to use. Okay, somebody asked, is it safe to dual boot Linux on a MacBook? Safe. Yeah, if you install Ubuntu 20, it should be fine. I don't know if you mean, is it safe for your machine? I think it's safe for your machine. Yeah, so this student who asked if it's safe to dual boot, do you mean, is it safe for your MacBook, or is it safe for this class to use a bare metal version of the operating system? Oh, I don't know. I can't help you with Mac OS support. Maybe they have some software called Boot Camp. I don't know if that supports Ubuntu or GNU Linux. Somebody asked, what's the purpose of VirtualBox and Vagrant? We'll go into that in the second part, but basically it's to number of purposes. One is to get you, this is your first piece of system software that you're going to learn about. It also standardizes the grading environment and the programming environment for all of us. Even though C is nominally a portable language, there are some minor differences between compilers and systems. I had a case a couple semesters ago where I think it was the TA's project. He had a program that worked fine, and when I ran it on my machine, compiled and ran on my machine, I had some null pointer error, and that's because of I had an uninitialized variable or someone, and so there's some undefined behavior that varies between compilers. So someone says if you have a touch bar with your Mac, there really isn't support for UBI. There really isn't support for Linux. Function keys in Linux are not strictly needed. I think you can get by without them. So somebody asked, do we need to create our own GitHub account to create compilers projects? You need a GitHub account. If you have one already, you can totally use that. Somebody said invitation not found message after clicking the GitHub link. Let's see. Is that happening right now? Invitation not found? Uh-oh. Which one are you clicking? Is it Simple C compiler? they're all working for me, I think. Yeah, they're all working for me right now. Let me. Oops, I should not show that. It has student names there. Someone asks, yeah, if we already have GitHub, are we just granting access? Yes, we are. Someone's getting a 404. I don't know what happens. Someone asked if we're gonna go over working with GitHub in the lab. We are 100% gonna go over using Git next week. How do we know if we've correctly signed up for the GitHub class? When you go to that URL and you have a repository there. I'll show what that looks like in the second part of this class. Oh, you get an error in Web Courses Preview, yes, because Web Courses does not have access to your private repository. Someone asked about the version of Virtualbox. You're using version 6.1.10 instead of 6.1.12. Probably will work. I just gave the versions that I installed. I tried to get the latest stuff. Okay, out of class contact. For out of class contact, I prefer Piazza, which I forgot to go through. Oh my God. So I skipped some slides accidentally. I just realized this. Oh, whoops. Oh yeah, I gotta go over that. I totally forgot about that. I hit the wrong button on my slides. They're in a two-dimensional plane. And, I'll go over the GitHub stuff. Yeah, this is the break. Somebody asked if this is the break. This is the break until 11:20. I totally should have gone over the actual course stuff. I'll do that when we come back before I go over the rest of the class. I think we should have plenty of time today. Okay, I'm going to take a 5-minute break and I will be back. This is terrifying. Like the Invisible Man. Here I am at HEC outside. Yeah, I need like a green screen or something. I like the headphones too. Someone asked, could we use EC2 instead of VirtualBox? It's a good question. Maybe. I mean, I think, don't you have to pay for EC2? Or are you just worried about your machine not being powerful enough? I mean, in principle, you could. I mean, we're going to grade on the platform that I give you. So if there's any differences or problems with that, then it's sort of on you to support. I mean, unless your machine doesn't support virtualization, VTX or something, just let me know in that case. Some funny comments here. This is a very interesting way to give a lecture. Oh, somebody asked how I do drawings. I use I have an iPad that I use for it, and I use an app. I use Notability. There's lots of apps for it. I have not made any podcasts waiting for class to be on Twitch. I mean, what's the difference? Yeah, I have terrible handwriting, so I type them. I can put like a text box and type them because my handwriting is atrocious. All right, it's 11:21. Let's restart. All right, hopefully everybody's back. Let's see how many participants there are. Wow, even more than when we started. That's good. Okay, so in the first half, we talked a little bit about the course structure, the syllabus, and my secret objective to make you a better programmer in this class. So it's not purely an academic exercise. I accidentally skipped over the mechanics of the course, all the tooling we're going to use. So first, I want to point out some of the changes I made from the last offering of this class. If you've asked any of your fellow students or anything about it, I do try to read feedback from. I mean, I do read the feedback from the students. I can't always address everything, but some of the positives I got was students really liked in-class coding and demos. So I'm going to try to do even more of that. A lot of in-class coding and just using the command line in class. I realized that students may not have had a lot of experience with these command line tools, and I was maybe expecting a little too much from it. So I'm going to just do all of next Friday is going to be, here's how you use command line tools. We're going to go over a whole bunch of them and try to help build up your muscle memory. So for the in-class coding, I really encourage you to just yourself type things out. Whenever I was trying to learn programming languages, I would just literally take example code online and just hand type it out. It's useful for getting muscle memory. Also in the previous class, I had you write the lexer and the parser, the first parts of the compiler, and these are pretty tedious and difficult to get right. So instead, I'm gonna give these to you, and that will let us to do a bigger language, more coding in the back end of the compiler. This also helps with one of the complaints that I got from students, which was that I cover things too quickly and maybe not enough depth, particularly the formal stuff. And part of the reason for this was that I had to give you this material in order to do the lexing and parsing, the first parts of the compiler. They're very theoretically driven, and I tried to fit in a lot of theoretical stuff very quickly. But by detaching it from the programming assignment, we'll have more room to cover these more conceptual theoretical topics. we're going to cover, and these are the new models of computation that I talked about in the first part. We're going to use these. These are actually what you'll learn about in big discrete 2. So it'll give you a little leg up if you haven't taken that yet. And you'll actually see a place where they're truly useful. They're not purely theoretical things. They're very useful models of computation. So that's some changes from my last offering. I've also changed up the programming assignment. I really wanted students to generate like real machine code and link with the operating system. So I've changed that up as well, and taking more from the front end away, giving you more of the front end makes that possible. And hopefully with this online format and the longer period, I'll be able to walk through things more slowly and more carefully. So I'll try to do that. All right, let's just go over some of the tooling we're going to use for this course. Being a totally virtual course, there's a few additional pieces that we're going to use. So there's kind of a lot here. It's kind of a lot that is kind of a lot of technologies we're using for this course. So it can get a little bit overwhelming, but let me go over these pieces here. So web courses is your main entry point to the course. Here I will keep links to everything else you need for the course. The front page of web courses here, this is the student view. This is what you should see in web courses. These are all the links you'll need for the whole class, for the whole semester. Web courses is also going to be used for announcements. You should have received a whole bunch of announcements this week. I've sent out a bunch on, updating modality and assignments. Given the participation count, it seems like almost everyone or a good portion of people have figured out how to get in with Zoom. I controlled access to only be for UCF addresses. But yeah, so web courses will be for announcements. You'll have assignments given there and the grades. And for written homework and logistics, you'll submit that via web courses. But for code, you'll submit that via GitHub. And the final exam, I think, will probably be through web courses somehow as well. Any questions? Any questions on web courses? I think it's pretty standard. I've gone over the course web page already at the beginning of the class. We'll do Vagrant VM setup today. So I've gone over the web page. So the web page is where you'll have the lecture schedule and perhaps most importantly, lecture notes. So each day will have its own link and its own notes, which are the web page version of the slides. They'll also have project descriptions, although they'll also be the assignment in web courses that'll just point to the project description on the web page. So that's the course web page. Zoom, of course, we're using Zoom to broadcast questions. So keep in mind that Zoom is a third-party service. There's no super strong privacy protections or anything. We're recording it so that other students can look at it, and also so that the courses, so my thinking is to make these publicly available. Pretty sure I'll do that. So keep in mind that it is kind of like a public forum. So if you don't want to be recorded, your voice or video, then use the chat to do this. Use the chat, because these are being recorded. And if you have anything to ask me sort of personally or privately, you can go outside of Zoom to do that. I will try to post the recordings pretty fast. I think with Zoom, I can just like publish them immediately with the cloud recording, but I haven't actually seen how that looks from your point of view yet. But yeah, I'll try to post these on web courses immediately, and they may be publicly available later. So some people are asking about contact with me. So let me go to that first. We're going to be using Piazza for content discussion. And I'm not sure if you guys have used this before. I've used it in the past for this course, and it's been pretty useful. It's been pretty successful, I think. You can make your questions public or instructors only. by asking questions publicly, you benefit other students, and you also save me and the TA from saying the same answer over and over and over, which is really useful. But me and the TA will, I go on Piazza, I'll go on regularly, at least a couple times a week, and answer questions. And also my email inbox, the longer I'm a professor, the more my inbox becomes absolutely insane. So right now I have about 400 unread messages and probably thousands of messages that I haven't organized. I used to pride myself on having an empty inbox, but that has become pretty much impossible. So sending me an email about course content will get lost. I'll try to respond, but if it's course content, then ask it on Piazza. But of course, for things that are sort of personal issues or questions that are not appropriate for a public forum, then certainly send me an email. I will try to get to it as soon as possible. But for course content, like this is breaking, or how do I use this piece of software, or when is this due? Ask on Piazza. Yeah, course questions, it works out really well. It makes it very easy for me to see what questions are pending. My email inbox is, you probably don't want your email there anyway. But if you have personal issues or some private thing you need to talk to me about, we can certainly use that. All right, so here's an interesting one. So any other questions on Piazza or about email? So for personal stuff, send me an email. Or tell me on Zoom, oh, I need to talk about this. I'm going to send you an email. All right, I think everyone's good on Piazza. All right, so for office hours, I was thinking about this quite a bit, and I thought that Zoom may not quite be the right thing, because it's sort of for you can have one meeting in Zoom per account, and everyone is on the call. So my plan is to use this kind of interesting piece of software that some academic conferences have been using called Gather. Who has seen this, or Gather.town? Has anyone seen this before? So I'm a little hesitant to, there are breakout rooms in Zoom, but I think I have to assign people or something. I don't quite understand it. So Gather is interesting. We'll see how this works out, but it's basically a virtual space where you get a little avatar, you move it around with your cursor, and when you're in close proximity with a certain number of people, it'll automatically create a group chat for just those people. And so we can try this out today during office hours. It is also a third-party service, so keep in mind this is, I have no idea where these videos, what servers they're going through, so do not assume privacy here. This is a public forum. But for office hours, I think that's appropriate because it kind of simulates what we have. Yeah, so Zoom, I could do this. I want to try this technology because it's basically kind of like we have in an office. I'm basically there in a physical space, and people come up and people can listen in if they like to. People can have their own separate conversations that are separate. And so all this is kind of possible in this Gather.town. So I'm using the free version of it. We'll hopefully we won't overextend what services they give us, but we'll try it today. So I'll have office hours at 1 today, and we can try it. It's this is for office hours only. So this is just for office hours. So as mentioned here, Zoom is for, oh, I didn't mention here, but yeah, Zoom is for lectures and labs, and it's the same link for lectures and labs. It's the exact same link for all of it, for every day. It's gonna be useful. Some people are making references to Second Life. It is kind of like that actually, but it's useful for group chat because you decide on, it's sort of allows you to do ad hoc group chat basically. So I don't have to sit there and organize you into groups. And if you want to talk to somebody individually, you can do that. Or if you're waiting in line, and often in office hours, there are some students who will provide excellent support helping others while they're waiting, which is really useful. So hopefully we can stimulate that experience. So let's try it. If it doesn't work out, then we'll see. We'll try it today and see how it goes. Hopefully we're not going to get, maybe a ton of people just want to try it, and then we're going to get like hundreds of people. Okay, and so the last piece of the puzzle here is GitHub Classrooms. GitHub Classrooms is for submitting code. And I'm going to go through this today, how we actually use this. But this is great because it provides a central place for me to have private repositories, for you to have private repositories, and for me to access them for grading. So I want to be really clear, any sort of coding does not go through web courses and should be on GitHub. And to be really, really clear, don't put any of your coursework in your own personal accounts, repositories. It should say, I'll show this in a little bit, it should say, you know, COP-3402 in the link. So keeping this code, like making this code public is definitely violating UCF's golden rule. So don't let other people copy off you, basically. I've been good about changing the project every semester, so it sort of cuts down on the apparently very common exercise of just taking old people's projects. Don't do that. Don't help other people cheat. You put a lot of time into making this work. Yeah, don't let other people copy your work. Yeah, I mean, I've seen for previous versions of this class, I've seen like whole code bases for the project online. Maybe I shouldn't say that, but yeah, my TA found these online. Okay, so all your code is going to be submitted via Git. We're going to go over next week how to use Git. This does require a GitHub account. So if you have one already, you can just use that. If you don't have one, please create one. Keep in mind, this is also a third-party service. So, you know, it's a third-party commercial company. So privacy is not, you know, it's not the best for that, but we're using course projects. I'm okay with using it for course projects. So that's just a requirement for this. If you have any issues with any of this, just let me know. Okay, so let's walk through submitting our first assignment. I call it an assignment because we need this for academic activity. So for those of you on financial aid scholarships, turn this in today. Yeah, you can use your personal GitHub account. Just don't copy the repository anywhere else. Just have it on your local machine, wherever you're working on it. Yeah, don't push it to anything, particularly anything public. So this is required for academic activity requirement. This is due today because I think the university requires it due today or maybe tomorrow. So I was hoping to just have everyone do this in class together. If you don't have a GitHub account, it might take you a second to create that. But if you haven't already, this literally takes 30 seconds. So I strongly recommend doing this today and submitting it, particularly if you need that academic activity required, because this is the academic activity requirement. Okay, so in our master page of links, this is the Simple C compiler link. You'll also see it in assignments. The assignment has this link as well. We should be able to just click on this. So this is saying it's created already because I already created it. Let me delete this and show you again what it looks like. You should probably actually type this out. Don't actually do this. Type it out because that's meant there to protect you from deleting stuff you shouldn't delete. All right, so this is what you'll see a little question that says accept. It'll ask for GitHub permissions for like GitHub web courses. If you don't feel comfortable with that, make a new account. And you'll see it'll create the repository and voila, it gives you the link right here. So this is the link that I'd like you to submit for web courses. You can go to submit, so just copy it, submit your assignment, put it in the website URL. It should have the form of HTTPS, blah, 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 github.com. It should definitely have COP-3402 Fall 20 as the organization, GitHub organization, and then it'll say simple C-compiler- and whatever your user ID is. Mine is Paul Gaz, so that's what my link looks like. Questions on this? I noticed a bunch of people already kind of submitted theirs, which is great. But that is literally your first assignment. That's it. Just takes a minute or two. So somebody asked, how can you tell if it's private? So for GitHub, if you create it through this link, it should be created as private. But in GitHub in general, they put a little tag here that says private next to the name of the repository. So you can confirm that it's private. I'll also see, well, yeah, I mean, we can also double check that everything's private. But if it's created through GitHub Classrooms, I've set it to be default to private. The invitation link, somebody asked about the invitation link. Above the link for my repo. What's your question? Somebody's asking about the invitation link. Is there an issue with the invitation link? The invitation link is here. Does that answer your question? Okay. I don't know what the question is. But if you have an issue setting this up, let me know. I don't know what that link is. There's another link. Should I just click on random links and see what happens? Yes. I don't know what the invitation link is. I wouldn't worry about the invitation link. Just use this link here. And so to show the student who's asking what it looks like, after you've set it up, this is what it looks like when you've accepted the assignment and they give you a repository. Somebody submitted their GitHub URL. Okay, so for particular issues, let's take it to Piazza. Let's take it to office hours, and we'll get everybody squared away with that. But I think a bunch of people have gotten this set up, so it might be some minor issue. Maybe you have to be. So I'm logged in already, which might help. Maybe if you don't need a particular username, you can use your own. You can use your own GitHub user account or a new one if you feel more comfortable. All right. Any other issues? Yeah, I guess you can just ignore that invitation link. Just create the repository and just accept the repository creation. It'll show you it's creating the repository, and then you'll get a link that you can use. Other questions on this? This is your very first assignment. Don't be deceived though. The assignments will get these are logistical assignments. They're for very small points. The real assignments will get challenging. Okay, chat seems silent. All right, let me go back to my slides here. So oh yeah, so I already went over the slides on my secret agenda to make you better programmers. No, you don't need to set up your local repository yet. We'll go over that next week. All right, so I wanted to go into a little bit about debugging and good software engineering practices. This is something I noticed that students, particularly starting out programmers, this is another thing that's sort of hard to cover in academia. That's sort of expected to. It's a part of the practice of programming that doesn't always come out unless you take maybe a formal software engineering class. So the first question that gets into this is, what is a bug? So class, what's a bug? What do you think a bug is? I'm interested to see your answers. A bug is bad. A bug is a compiler error. That's an interesting one. An error. Well, that's sort of paraphrasing. A bug is annoying. Logic error. Logic error. Okay, that's a good one. We'll get to that. Ooh, unexpected or unintended behavior. That's a nice definition. When the program is giving unexpected output, something that shouldn't be there, a mistake in how the code is written. When the code doesn't do what you think it does. Oh, okay, these are great. A bug is a bug in a vacuum tube. Oh, okay, that's like the possibly apocryphal story about a physical bug being in, and that's like the origin of the term. I don't know if that's actually true. Something that prevents your code from running as expected. They must be eradicated. An insect. Okay, yeah, these are really good answers. So probably a good portion of people gave the answer that I would give. But to first motivate this for those who haven't thought about this or haven't used the definition that I'm using, let me say what a bug isn't. So a bug is not the program does something wrong. The program, so for most cases, when you're writing code and you compile it and you run it, the code is doing exactly what you told it to do. It's doing exactly what you wrote. There are rare cases of this that I'll get into where that's not the case. But almost always, particularly for students starting out in programming, the program is not doing something wrong. And so I really want to like disabuse you of this notion that the code is, this is like anthropomorphizing the code. The code is not some self-aware agent, at least not now. The code is something that you wrote. And if it does something wrong, it's what we wrote that's wrong. So the bug is not the program is wrong. What a bug is exactly what some of your classmates said. A program that does what it's supposed to do, but not what we think it does. So another way of putting it is the program does something that we don't expect. But to put a finer point on it, the program is doing exactly what it's supposed to do. The program is not wrong or broken. The program is not buggy itself. The program doesn't have a bug in itself. It has a bug because there's a gap between what the programmer thinks it does or the user thinks it's supposed to do and what it actually does. So what do you guys think of this definition? Is this new to anyone, this notion of bugs? Does anyone think this is new? Did you guys learn about this before, I hope? Okay, that's good. So for some people it's new, I hope. So it's just, yeah. So when you come to a program and it's not breaking, yeah, I think, well, there's a lot of sort of definitions about what a bug is. But if you see a program that's where its output is not what you want, it's not really the program's fault. It's the programmer making a mistake. And the program is not wrong. The program is doing exactly what it's written to do. The problem is that it's our expectation about the program that is not matching the physical reality of the program, because the running program is a physical device. And assuming there's objective reality, that physical device is operating independently of our minds. And so when the program does something unexpected, for when we're coding, it's often the case, usually the case, that it's our thinking about the program that is wrong. And so without action at a distance or mind over controlling matter, that code will just operate in the real world, and our expectation, just because it doesn't match it, does not affect that program's behavior. All right, so there is a big exception that someone pointed out, and that's bugs in the compiler or the system itself. An exception to the notion that a program always does what it's supposed to do. So this is an interesting point that we'll get to when we're writing our compiler, that if you have code as written that's supposed to work a certain way and you've debugged it and looked through it and it's still giving you unexpected behavior, it might be that the compiler was broken. Because as we'll learn in this class, the C code that you write, the programming language that you write, is not what actually gets run on the machine. There's no hardware that I know of that executes C code. The C code is designed and, from what I understand, always translated into machine code. And remember, the compiler itself is a program, the program whose input is some other source code and the machine code as the output. So if there's a bug in that process, that is, the translation from source code to machine code has some unexpected behavior that the compiler writer didn't expect, then the program that you wrote in C, even if you wrote correct C that matches exactly your expectations, the output program, the machine code, may have a bug introduced by the compiler. So there's a whole industry of both in the industry side and academia in getting compilers right. There's a very famous speech by, it's either Ken Thompson or Dennis Ritchie, one of the two, about reflections on trusting trust, about how you can basically use a compiler to, own the security of a system, and this problem of bootstrapping compilers. If you're interested in that, let me know, and let me know later. I'll send you the paper to that. But it's a very cool paper, very short, that he gave during his talk from his Turing Award acceptance speech. But yeah, trying to get the compiler right is really, really hard. And when it affects the correctness of the translation from C code to machine code, yeah, it can be a huge problem. But for most of us in this class, we're writing the compiler itself. So we can usually trust GCC to compile our compiler correctly. So most of the time, it's going to be our problem, our fault when we misprogram the compiler. There can also be hardware problems. So as a software guy, I take the hardware kind of for granted. But sunspots can cause bits to flip in a processor. Overheating can cause the machine code to actually give the wrong instruction. Overheating can do this. So there are the entire computing stack. There can be that each of those systems were implemented by people, and they can have their own bugs, their own gaps between the expectation about what it's supposed to do and what the actual implementation does. Somebody asked if GCC is only for C. Historically it was, but now it's the GNU compiler collection, and it supports other programming languages. We'll get into the front end versus back end, like how a compiler can support multiple languages. We'll go over that when we talk about compilers. But basically you can design a compiler to be able to support multiple front end languages and multiple back end languages, which is what GCC does. Okay, so here's a little 3-step process for debugging. So for some of you who have experience programming, you may have kind of figured this out. But those of you who are a little newer at this, this is something that's really going to be really, really useful. So if you find a bug and you're really frustrated, you find that your code is not doing what you want it to do, and you can't get those pixels on the screen to look the way you want, here's a process for getting the code to do what you want it to do. So step one. So somebody said step one is Stack Overflow. Yeah, they're wise to programming for homework assignments. So Stack Overflow is not going to work so well. So this is if the code you thought was written was correct and it's not doing what you expect. So the reason that you think it doesn't do something right is you have a test case. You gave it an input and the output is wrong. You have a null pointer error, or the output doesn't look right. You have a logic error because even though it doesn't crash, it's not the right output that you expect. So the very first thing to do is to narrow down the problem by limiting the test case. Craft a smaller version of the test case. For some applications where you have simple inputs, maybe you can't do this very easily, but for a compiler, the input is literally an entire program. So the first step is to narrow down this program to get the smallest version of the test case that still causes the bug. Now, if you have multiple bugs in your compiler, it might be difficult to zero in on the same bug, but narrow it down to the smallest test case that you can possibly create. Okay, so why do this? The reason for this is that if you narrow it down, then that'll allow you to figure out where in the code that must be related to the problem. So if you have a giant simple C program that's using every part of the compiler, it's very, very hard to narrow down which part of the compiler that is being touched. Now you can also use a debugger to help you do this as well. And I'll show maybe quickly how to use GPB for this, but I don't think you need to use a debugger really for this necessarily. So narrow down the test case. Use that narrow test case to identify where in your code the problem is likely related to. And then step 3 is the most important part. Once you've localized that bug, where in the code it's most likely occurring. This is the most important part. And this is where knowing your language really, really helps. Trace that code step by step to see what it really does. Don't trace the code saying, oh, I wrote this before and it was supposed to do this. Don't think about what you hope or feel or guess or intuit what it does. Instead, treat it as if you're the machine and you're executing that code to see what it actually does. And so the reason for this, as I hope you can imagine, is that this ensures that you have a view of what the code actually does. Because remember this definition of a bug. The bug is a gap between what the programmer thinks the code does and what the code actually does. So in order to resolve the bug, we need to know what the code actually does. I know a lot of sort of, when you hack together code, it's very tempting to do the kind of, 100 monkeys at typewriter approach, where you have a couple test cases, you run them, and then you say, well, maybe changing the code in this way will fix it. And then maybe it fixes the test case, and you do it. I mean, that can work for sure. But I would say take the laziness virtue that Larry Wall pointed out and say, do you really want to sit there and just randomly mutate code and see if it works? No, you can automate that. There are systems that will automatically, first of all, generate inputs to break your code. And there are systems that will automatically synthesize new code and see if it works. You can automate that. So somebody feels called out by this. So it's definitely not any one individual. This is everyone who is like ever programmed, myself included. Yeah, so anyone who's ever programmed has tried to do this. And it certainly works for small programs. And that's why it's actually, there are tools that automate this process of saying, I don't care how the code works. Let me just throw inputs at it and let me just kind of randomly mutate the code. But what I'm saying is be lazy. Don't do that. That's boring and tedious. A computer can do that. Why should I do it if a computer can do it? Somebody asked a really interesting question, which is, for more complex languages, is it harder to understand the inner workings? Yes, yeah, it is harder to understand the inner workings for complex languages. When you have more constructs, when the language is doing more for you, it's harder to understand it. For sure. I mean, they're going to be more complicated to understand. But it's not necessarily harder to understand from a high level what the constructs do. So you can kind of understand abstractly what the programming construct does without having to understand how it's actually implemented. And actually, we'll get to that. And actually, this brings me to exactly to the next point, which is that the academics and the software engineers have some kind of formal terminology for this notion of a bug. And that's the specification versus the implementation. And these fancy polysyllabic words really just mean what we want our program to do, what we expect it to do. That's the specification. And what our program really does, that's the implementation. And so we can reframe or rephrase this notion of a bug as the specification and the implementation don't match. Our implementation does not match our specification. It's the same thing as saying a bug is when the program does something that we don't expect, or what we want the program to do is not what the program really does. We can make fancy polysyllabic terms for this: specification, implementation. All right. So the goal of coding, I mean, really, you can almost say the goal of all coding is to make the implementation match the specification, to make the program do what we want it to do. Now, this is super easy to say, and when we have this nice polysyllabic words, it sounds all impressive, but it gives you no indication about how to actually do this. And there's a really good reason for this that I observed while thinking about this lecture, that when you're writing code, especially for a big project, the implementation never matches the specification because the code's incomplete. So if you're taking weeks to write code, it makes no sense to say, well, just make the implementation match the specification. How's that possible? Because while you're writing the code, the implementation never matches the specification. Now, as a young programmer, like most of you, the intuitive way to get a program done is, okay, here's what I want the code to do. Now let me just code for like several hours or several weeks and just get it done. And once I finish writing it, now I've got a program that matches the specification. Okay, I tried testing it on some inputs. It broke a little bit. So let me go down and let me debug the code and try to get it right and go back and fix things up. So that's a very simple sounding approach, but this quickly snowballs into a really, really, really hard problem. It works for small code, for sure. But think about it this way. If your program has, say, 3 if-then-else statements in it, then how many different paths through those if-then-else statements are there in your program? Let's see some answers in chat. I got 3 if then else statements in a row in my program and some, other straight line code. How many different paths through those if then else's? 8. Good. I don't know, like 18. Okay, you're 10 away. So 2 to the 3, right? I mean, there's 2 branches on each. And so that causes 2 times 2 times 2 different ways to go through that code. So if I have a larger program and now I just have, if I increase that to just 10 if then else statements in my code, how many paths through that code are there? 10, 24, 2 to the 10. So if you write a whole bunch of code and then you go back and run test cases and check it when it's done, you've just given yourself potentially thousands and thousands of flows through that program that you have to go through the debugging process of, oh, let me narrow my test case. Let me see where in the code it might be. Let me now trace the code. Okay, I don't know which branch this is caused by. You've given yourself actually a much harder problem. And so this violates the virtue of laziness, kind of unintuitively, because it seems lazy to just sit down and code it in 3 hours and then I'm done, I submit it. But it turns out that when you're making substantial software and you want it to be correct, doing it this way actually makes it harder and makes it longer for you to code. So there's a kind of related quote, a really nice quote by Byron Kernahan from another classic book of his, Elements of Programming Style. And the quote goes like this. Some of you may have heard this. He says, everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? And this is an excellent point, because rather than using cleverness to write the code in the first place, let's write very, very simple, straightforward code and use all that cleverness for something else that's going to actually decrease our energy expenditure. So take all that cleverness. A lot of you are very smart, motivated programmers, and you can sit there and you can just pump out really good code. And even if you can do that, I'm going to sort of encourage you to apply all that cleverness to designing and incrementally developing correct software instead. So let's be lazy. How are we going to, this doesn't solve the problem of, this doesn't really solve the problem of how do we get an implementation to match the specification? So even if we know that, debugging is really hard, the implementation doesn't match the specification for the entire development time. The specification is not done yet. So how do we do this? Well, let's take a lazy approach. Instead of having an incorrect program that doesn't match specification and just leaving it incorrect the entire time you're developing, let's take a lazy approach and just say, well, I don't want to write that whole program. Let me just write a really, really simple part of that program. When I have to write like a new project, I will literally write a hello world program because I want a program that I know works. And even though hello world program is very, very far from what I want for my full specification, it's something I know I can get working. And then once you have that simple part of the specification working, don't gradually expand the implementation. Well, you have to gradually expand the implementation, but gradually expand the specification that you're working with, always keeping the implementation correct at each step of this. So leave a very, very short period where the implementation does not match the specification. And I'll go over some tricks for making sure that your program is really within those bounds of specification. So there are some styles of programming where you either put runtime checks, you can think of this as a form of defensive programming. But instead of defensive programming to protect against inputs, defensive programming to protect against running part of the specification that hasn't been implemented yet. So when we're writing our code, we'll see when we write our compiler, but there are times where we just, me or any programmer will not have time to finish the entire part of the project. So we can put little checks that will make sure that if we have an input that has one of those, that's part of the specification we haven't implemented yet, then the program will crash explicitly. So somebody mentioned before about logic errors. So who's heard of logic errors before? What's a logic error? The person who brought that up, what did you mean by logic error? Maybe that person left. Okay. So logic error is one where the program, the program, so basically there are two kinds of errors you get in code. One is trapped errors, those that halt the program, where the hardware itself throws a fault. That's like a segmentation fault, a null pointer error, some memory exception. Yeah, logic error is one where the implementation doesn't match specification, but there's no hardware crash, there's no fault. So one little trick is when we narrow the specification, for the rest of the specification, we implement the code, but we implement it to just crash. And that way, when we run the program, if we give it an input that we weren't actually supposed to be working on yet, the program will explicitly crash. So we've turned that logic error, which is very hard to track down, into an explicit crash. So it's not, I mean, it's not even like a crash in that sense. Formally, it's called like an assertion error. It's making sure that the code only does what it's supposed to do. And for those parts of the specification that aren't done yet, one useful trick is to turn that into an explicit crash by just writing out an error message and saying exit. So it's not really a crash, it's the program exiting, but it's the program exiting in an error state, an explicit error state, so that you know the difference between here's the specification that has been implemented and here's what hasn't been done yet. And that really helps avoid this problem of I'm expecting the whole specification to work, but the implementation is either narrow or flawed. And so when you give the test cases as input, you won't just have a silent failure. A logical error is a silent failure where you have to just manually check the input and output. This is a very useful technique, particularly in compilers where we have a lot to write in order to get the specification right. Okay, so that was a little bit of a separate rant on logic errors, but the whole point is here, let's be constructively lazy and just give ourselves a narrow specification. And then here's where all that cleverness comes into play. Instead of applying that to making the implementation match specification, apply that cleverness to find ways to break the problem down into smaller pieces, to break that problem down into individual specifications that you know you can get right. Someone said merge sort, so exactly right. So we're going to talk about this. So merge sort is a divide and conquer algorithm, but we can kind of extend this notion of recursive problem solving and having separate functions do work for us. Merge sort is a sort of a complicated recursive version of this, but we're going to turn this broken down specification into basically function abstractions, into an API. But yeah, let me talk about that in a second. So the idea is to break down the specification into smaller pieces. Now this is hard to do. I don't know if anyone's really automated this yet. Maybe at some point we can automate this and apply our cleverness somewhere else. But right now in coding, as far as I understand, this is where we really need the cleverness, to have the right problem breakdown and the right design of the solution. So this is really tricky to get right, because if we try to generalize prematurely, we can waste our effort. If we just think, oh, well, here's the function I need, and then spend 10 days writing that function, and then it turns out that it's not really implemented the way we need. Even if it matches the specification, maybe it's not the right specification we need. So this really just takes some experience. Doing a compiler is a good way to do this because it's a very challenging problem, but the phases of the compiler, the breakdown of the compiler is well known, and I'll give it to you. I'll give you the phases of the compiler to write. So we'll have a clear interface between these pieces of the compiler. Now, the other important takeaway, so if you take away like anything from this class, one is this definition of a bug. The second thing is revisit your code. Don't be afraid to refactor. The only way this works, breaking down, getting the specification right by breaking it down, is that you write something, and if it doesn't work exactly the way you want it to, even if it works correctly, if the specification wasn't quite right, the design you made, don't be afraid to go back and refactor the code. You wrote the code. You don't have to be stuck with it. You're not forced to use that code. You can rewrite it. And it can be maybe intimidating or feel hard to have to go back and rework code because you thought, oh, that was so hard to do in the first place. I don't want to even go look at that code again. But if you're taking this approach of breaking the problem down into really simple parts, then it's no problem to go back and look at that code. That's another reason why you should, instead of applying the cleverness to writing the code, apply it to the specification so that the code will be really, really simple and comment it. So you can go back and be like, oh, I need to change how this code works. Let me see what I wrote before. It'll be very easy to look at if you write it very cleanly and simply with comments. So it's sort of kind of a principle of software engineers that it's much easier to reorganize code after prototyping it than it is to write a program from scratch. Generally, this is true. I mean, sometimes when you refactor, you may end up actually rewriting the whole code. I mean, I've done this many times, but it's way, way easier to do that kind of incrementally through refactoring than it is to just start a new project from scratch. All right, any questions so far on this? Hopefully this is some good insight. I'm sure some of you are aware of this already. This is nothing I invented. This is what practicing programmers have to deal with regularly. Any questions so far? All right. So this is all kind of conceptual, that we have the specification of the program. It's just written in human language. Oh, this is what I want my program to do. But if we can find some, how do we define what it is the program should do, and how do we break it down into pieces and implement those individual pieces? So the key thing, probably the most important thing that a programming language provides, because keep in mind, you could just write in machine code and have equivalent programs. What the program language provides you is methods of creating abstractions. Abstraction is another fancy polysyllabic academic word, but an abstraction is a really, really simple thing. And it's something that I'm sure, I know every one of you works with every day. So what is an abstraction? Abstraction is just something that hides unnecessary details and exposes some clear, simple interface to those unnecessary details. So I know all of you use abstractions every day, because all of you use at least cars, locks, electrical sockets. I'm sure all of you use at least one of these regularly. All of these are physical examples of abstractions. So think about a car. Probably most of you don't know the details of how a car works, or maybe you know conceptually, but you don't know the technical details of building a car. But that doesn't stop you at all from actually operating the car. So why is that? That's because all of the technical details are hidden behind the dashboard and under the hood and under the carriage. And what's exposed to you by the designer of the car exactly is press floor pedal, car goes vroom vroom. That's how the car works, right? So that's how the car works from an interface point of view or an operational point of view. But it's not physically how the car works. The car doesn't physically work by pressing the pedal, because if you have if you think about the famous case of the cargo cult, where if you just build the shape of a car and you put a pedal on the floor, the car's not going to go anywhere, because that's just the operational or abstract operation of the car. And humans are so human. So somebody made the good point that mechanics should know how a car works, like a programmer should know how the compiler works. That's exactly right. So a mechanic compiler writer, a programmer may not need to know how to build a compiler, but it's a useful way to do it. Just like a mechanic may not be a mechanical engineer, but they need to know the internal operation. Yeah, anyway, I lost my train of thought, but humans probably have some inbuilt ability for abstractions. I'm not a cognitive scientist, but I'm assuming that we have some inbuilt ability for this. So abstractions are so ingrained in us that we don't even really notice. So just like, I know it's kind of a joke from one of the students, but if you ask somebody, how does a car work, and they're not a mechanical engineer, they're going to tell you the abstraction. They're going to tell you the interface. They're going to say, I turn the steering wheel, I press the pedal. That's not because they're stupid or because they're not educated or they don't know, why should they have to know mechanical engineering? That's because humans are actually really, really smart at using abstractions. We can use this very sophisticated technology by just operating an abstract interface. And I don't think that's stupid. I think that's actually incredibly smart. I think that's what humans I don't know if it's humans exclusively, but humans have this very seemingly special ability to operate using just abstractions. Now, it can be a problem, like somebody said, for programmers. If you don't understand behind the abstraction, it can make it harder for you to do your job. So just like a mechanic really should know how a car works to work on a car, if they're just following a manual and not actually understanding why those procedures work, same way a programmer really should understand how the machine works in order to do programming. So this, again, these are kind of academic terms, and this is all kind of loosey-goosey, because saying how do you hide unnecessary details and expose an interface, again, that's super easier said than done. But one little tip here is that the decisions about the interface for good interfaces are determined by the use of that abstraction. So you could imagine a car designer putting the steering wheel, just operated by the right hand, and both the right hand does the gas and the steering wheel, but the left hand does the clutch and the brake. That might be a poor design. It might work. It might be an abstraction, but the interface design is designed around humans, how the human body plan works. So in the same way, when we're using computing, the programming language is designed around the way humans think. We think in abstractions, so the programming language gives us abstractions. And when you're building software, you're not just making user level abstractions for the user. In order to break the specification down, you make your own layers of abstraction in your software. And when you design those, you design them to make it easy for you to write the code. So you don't just write an abstraction because you can. You don't write an abstraction because, oh, I want to stop duplicating code here, or I want to have one function that does everything for me. You write abstractions that make it easier for you to write the program. That's the laziness virtue in programming. So anyway, we're going to see a lot of this when we look at the compiler. And when we code together the toy compiler, I'll try to go into this about how you design abstractions for laziness to make it easy for you to do your job. So if you break the program down right and you design the abstractions right, it'll be really easy to do the conquer part and bring together your code. All right, and I know this is all very much conceptual. We'll go into practical detail over the next couple of weeks. All right, the most important abstraction, probably the most important abstraction in all programming languages is the function abstraction. In fact, it's so common that you probably don't even think about it as an abstraction. You just say, well, this is how I write code. I write this in a function. But it's an invention. It's a human invention. The machine, just like recursion, the machine itself does not have any notion of a function. The machine just runs straight line code and does branching. That's basically what you get in the hardware. The function abstraction is a conceit by programming language designers. And the function abstraction is really it's one of the most common, and it's really one of the most powerful and most useful. So what is it? What does it do? It allows you to give a name to a snippet of code. So that's hiding the unnecessary detail behind a name. And humans probably have some inbuilt language ability. And this notion of naming and using naming as an abstraction is something that humans are just really good at. So this notion of a programming language is an interface that's very human-centric. So a function allows you to give a name to a snippet of code to hide all that detail behind a name. But it's not just a name. Probably the most important part is that it provides you a definition of the input and the output. Now, for statically typed languages like C, that definition even has some machine-checked part of the definition. When you give the type of the input and output, you're restricting the data that can go in and out of that function, automatically restricting it. We'll talk more about type checking in like a month or so. But really, the specification is done in the documentation of the function. It's the API documentation. And so even though that's in human language, that is the description of the abstraction. There are efforts to make these kinds of descriptions machine checked and formalized. But for our purposes in C, what we get is a named function that has typed input and output, but it's your job as the programmer to provide comments and documentation about how that function should be used, what its API is, what its interface is, what does it expect as the input, What does it give as the output? And remember, when we're trying to make our specification match our implementation, our specification should include error states. It should include the errors. So when you define that input and output, define all the possible inputs and define all the possible outputs, including which outputs are errors. And this is not just an academic exercise. This is useful for you as the programmer. When you design your mini specifications, your abstractions, you write documentation so that you remember how to use it. And if you want to take some shortcuts in your interface, that's fine, but just document it. That's going to save yourself a lot of pain in the future. And so in this class, we're actually going to implement functions themselves. We're actually going to see how the compiler makes functions emulated on a machine. And not only functions, we're going to see how recursive functions are actually implemented on a machine. So the machine code itself does not give you, I mean, Intel gives you a little support, but it really gives you compiler support for functions. But in some simplified sense, the machine does not give you functions, does not give you recursion. That is a conceit by a programming language designer. And it gives us a way to write abstractions, use abstractions to write our code. And we're actually going to see how those functions are implemented. Okay, so let me speed this up a little bit. But so I kind of touched this already. You break the program down, you make abstractions for those partial specifications, and then you combine them together to build a large piece of software. Abstractions create individual software components. Those are little kind of mini programs. They can be tested on their own. So if you've heard of unit testing, when you create these abstractions and you create software components, you can actually test that piece of the software on its own. So you don't have to try to track down a bug in your whole piece of software. You can just track it down, get it right in the component. Because you're using abstractions, you yourself can just forget about the details of what you wrote as long as you thoroughly documented and designed that interface. And then just compose your large piece of software by creating many layers of this abstraction. And if you take OS, I'm teaching grad OS next semester, if you take that, we'll see how the software on any computing device is built from a hardware layer and then gradually building layers of abstraction in software on top of that until we can comment on Reddit through a browser. But all that is like lots and lots of little layers of abstraction that have been carefully designed by engineers who don't want to have to think about, how do I comment on Reddit? There's millions of lines of software, maybe billions, that are responsible for that happening. No one person can reason about that altogether. Okay, so to wrap this up, bugs are not wrong programs, but incorrect assumptions about what the program does. To build software correctly and big software correctly, break the specification down into simpler specifications, use abstractions to define those specifications and implement just those specifications, combine those abstractions together to build larger programs. And this is really, really hard to do on small 100-line programs. It really is not necessary. Because you can just write skilled programmers can write small programs correctly in like 10 minutes, 100-line program. But when you get to large programs, it exceeds the bounds of probably any human mind to do, and that's where these techniques come in. And for our compiler, we'll really, really have to use these techniques to get a correct compiler done. Otherwise, it's going to be painful. I want this to be challenging, but not like futile. And if you use these techniques, and we'll go over it in a couple weeks, then it will be an easy and much more pleasant experience writing this software. All right, question. So somebody asked how many lines will a compiler be? That's a good question. I don't know, maybe 1,000? I don't know. I'm going to give you some code to start with. I'm going to give you some code, which is already several hundreds of lines. We're going to use tools that actually generate part of the compiler. So that'll be fun to see. So we actually have compilers. We'll see how that works in a couple weeks. But the total compiler with all the generated code will probably be a couple thousand lines. But the code you write, yeah, maybe 1,000, maybe 1,000, 2,000. I'm actually not sure. I haven't finished writing the compiler yet. Okay, other questions on that? That was kind of a long diatribe. Oh, good question. Any C concepts we should brush up on? Oh, yeah. So recursion, data structures, yes. You should be comfortable with recursion. You should be very comfortable with structs and linked lists. For better or worse, our implementation is in C. And when I go to write it, it's a little annoying to have to do data structures in C because we don't have these nice high level abstractions. Object orientation is actually super, super useful. I know there's a lot of, keyboard warriors who like to talk about OOP as BS, but when you get to large engineering, it actually is just a technique for defining abstractions, which is really useful. So you should definitely be comfortable traversing linked lists and traversing trees recursively. That's probably going to be like 90% of what we're going to be doing, or at least the coding skills. But we're going to have a lot of practice doing it. We're going to get a lot of practice. So CD8 concepts, somebody asked about this. As I mentioned before in this question period, we're going to be doing assembly in the second part of the compiler. We're going to be doing assembly. Yeah, there's a lot of hate for object orientation. I don't know. I think anything that's sort of popular or commercial gets a lot of hate. And there's certainly places where it's one model it's basically a way to model data structures. So not all problems require that. Some structures don't need OOP. Maybe you're doing data analysis and you need a different model. It's really, that's one of the things I want to get across in this course, is that there are various mental models for computation, and you pick the right one for the job. For compilers, objects and recursion are very convenient for compilers, and some other mental models we'll look at for particular pieces of the compiler are really useful for it. Somebody said real engineers write in Cobalt. Maybe you meant COBOL. COBOL is more of an application development language, but maybe Cobalt is something I'm not familiar with. All right, so that's it for my diatribe on bugs, specification for implementation. I'll try to tie back to this as we, I want to actually show you coding and how it kind of show you examples of thinking about this, so it's not just purely conceptual. All right, so this is the last portion of this course, setting up your virtual machine. This is assignment 2. It's just a honor system assignment. You set it up and you just say yes in your assignment. So if you lie and you don't have a virtual machine, you're going to have a hard time actually doing the programming assignment, which is 60% of your grade. If you want to not use a virtual machine and do something else, I really recommend that you do. Then let's talk privately in office hours and see if there's something set up. But it's a risk. If you don't use a virtual machine, it's a risk that our grading will not grade the program that you think it is because of differences in compilers and systems. All right, so this is the very first piece of system software that we're going to explore in this class. We're not going to go dig too much into the details of system software besides implementing a compiler, but we're going to use a whole bunch of system software. We're going to look at from the user interface point of view how to use the system software. The virtual machine is the first thing that we're going to look at. Virtual machines, well, once a more probably less common for PC users, has exploded. The industries for virtual machines is a huge industry, largely driven by cloud computing. Basically, the entire cloud infrastructure runs using virtualization. All right, so what is virtualization? Virtualization is taking a piece of hardware and emulating it using software. So for those of you who have ever done video game console emulation, you don't have to admit it. I mean, it can be used for piracy, but it doesn't have to be for piracy. You can emulate your own games. There's also a really cool website, Internet Archive, which has taken a bunch of free and open source arcade and game console emulators and ported them to run in the browser. So, emulation, video game consoles can get a bad rap from video game manufacturers because of their possibility for piracy, but there's absolutely legitimate uses of this. So this is used for software preservation. So for those of you who are interested in this, you're probably familiar with video game emulation. But those of you who are not, they've taken say they take an old arcade game. Someone looked at the actual hardware of that, and they wrote a piece of software that simulates what that hardware does. So if you get a piece of machine code intended to be run on, say, a Nintendo 2DS or an original NES, or one of these old platforms, an Atari, if you get the machine code for that, normally the hardware would process that machine code and give you the output that you want, give you the pictures on a screen or take the input from a controller. But a piece of software can also read in that machine code and perform the exact same operations, behavior that that old hardware would do, but do it on your new hardware. So it provides this layer of abstraction away from the hardware that takes in the original hardware's machine code and pretends that it's, tricks the original game into running on the original hardware. And because the application is just using the hardware, using the ISA, using machine code as the interface, applications usually cannot tell the difference. As long as the hardware is as long as the virtual machine is faithfully emulating the hardware, the application can't tell the difference. There are, of course, exceptions to this. So the old Game Boy, for instance, had a console that could print and take pictures. So if your Game Boy emulator is not emulating that part of it and emulating the actual hardware that did printing and cameras, then the application is just going to break. That machine instruction is going to return some unexpected behavior. Okay, so here's the example. I encourage you to check out the site. The Internet Archive is a great place. I actually donate to them. I think they provide really useful. I think they're a really useful public service. If you've ever heard of the Wayback Machine, so you can go look at people's websites from 10 years ago and the stuff they tried to hide. It's all archived in the Wayback Machine. Same organization. This effort was to take free and open source hardware emulators and basically port them to JavaScript in the browser. Kind of crazy that it actually works, but they've done it. They even have some old old Intel and Windows machines being emulated in the browser. Yeah, so people are making Oregon Trail, classic. All right, so some terminology behind virtual machines. The host operating system emulates the hardware of the guest operating system. The host is your operating system running on your native hardware, Windows, Mac, Linux, GNU Linux. The guest is the operating system running on the emulated virtual machine hardware. That virtual machine hardware runs on your host, and then the guest operating system runs on that virtualized hardware. Now, these days, virtualization has become pretty sophisticated. And so now there's actually hardware support that enables the guest OS to run most of what it does on the native hardware. If you're interested in that, take like an operating system class or learn, just read up on hypervisors. Very cool technology. But yeah, so doesn't just purely have to be software emulation anymore. There's support to allow the guest OS to run most of what it does on the native hardware, as long as, that's only the case when you're emulating a similar type of hardware, which is common in cloud computing. All right, so in order to get our virtual machine stuff set up, there's two pieces of software that we need to install. One is Virtualbox. This is the hardware emulator. This is the actual virtualization package. I've used the latest one. I installed it on my Linux machine, even though I'm already running GNU Linux. I'm still running an emulator just so I have the same environment as everyone else. Just go to your system. Should be straightforward to install. My TA tells me that he had no problem installing this on Windows, on his Windows laptop. So that's the first thing we need to install. Whoops. The second thing is this tool called Vagrant. I saw that some of you have heard of this. This might be less common for most of you. Vagrant is a virtual machine manager. It allows us to create, destroy, and work with virtual machines on the command line. I love working on the command line, and I'm going to have you work on the command line as well. I think it's an important skill to have, even if you go use GUIs in the future. So this allows us to fire up and use our virtual machine straight from the command line. So again, it's got installers for all the major systems. I've got it work. I had no problem on Linux, GNU Linux. My TA installed it on Linux. So somebody said, I hear a lot of people prefer Debian. I actually prefer Debian as well. I had trouble getting a pre-made a pre-made virtual machine, which are called boxes in the Vagrant world. A pre-made virtual machine that had Debian, that had the kind of features I wanted for it. So Ubuntu provides a lot of, it's a commercial company. They provide a lot of support and pre-built pre-built operating systems that are convenient. So I actually do like Debian as well. Ubuntu is basically built on Debian's tools. But anyway, this is GNU Linux distribution talk. Let's forget about this. Install these 2 pieces of software, get them installed, and then here is how to actually use Vagrant. So here's a system I've already installed with both Virtualbox and Vagrant. The first thing to do is to get the Vagrant file. I've provided a link here to it. This is my Vagrant file. Let me actually show you in an editor. It's probably easier to see. These are my notes. That is the wrong screen. Sorry, I'm jumping around here a bit. Okay, let me show you what this Vagrant file consists of. It is almost entirely comments. All these hash things are comments. There's really only a couple relevant lines. This is the pre-built virtual guest OS that you can download. It's Ubuntu. It's the latest, from 2020. People are asking about older versions of Virtualbox and Vagrant. It'll probably work. You have to be really careful that the Vagrant version supports the Virtualbox version. I just installed the latest 2 and it worked. But older versions of Vagrant only support older versions of Virtualbox, so be really careful with that. So this file just says which virtual machine we're going to install. It's a pre-built operating system, virtual operating system from Ubuntu, and it also provides provisioning information. This will automatically install all of the software that we need to, all the system software we need to work in this class. You can see it has Git and Make. It's got Build Essential, which is GCC and other tools, some editors. And when the virtual machine gets, well, let me actually show you firing this up. So when you're in this folder, you download Vagrant file to wherever you want to work on your source code for the project. Wherever you want to work on it, download it to there. Open your command line shell. This depends on your system. So command prompt in Windows, terminal in Mac OS, terminal in Linux. I'm assuming you know how to at least get into your command line and navigate to a folder in there. If you don't know how to do that, come to office hours, we can walk through it. So typically you'll start out in your home directory and then just change directory to wherever, CD for change directory to wherever your Vagrant file, wherever you downloaded it to. And it's very simple to use Vagrant. We're going to type Vagrant up to start it, and then Vagrant SSH to enter our virtual machine. So I just want to show entering the virtual machine first and the folder syncing before I actually show you what it looks like to actually fire up this virtual machine. So when we log in at first, we get this command line prompt that makes it very clear we're in Vagrant. Our user is Vagrant, and our machine name is Ubuntu Bionic. We are currently in our home directory, and I'll go over these commands next week. But the main thing I want you to be aware of is that Vagrant will, by default, map this folder /Vagrant to the host OS. So the guest OS's folder is mapped to the host OS's folder. What this allows is you to do your development in your host OS with whatever tools you feel comfortable. And then when you need to compile, run, and submit the project, you can do that all in the virtual machine without having to set up a GNU Linux environment or the right tools on your host machine. So I've created a file here on my Vagrant machine, on my virtual machine. So here I'm in the virtual machine, and I've got 2 files in the /Vagrant folder. I'm going to leave the virtual machine, Control D to leave or exit. Now see, I'm back on my host machine now. And if I look at the folder, I now have this hello world file. This works bi-directionally. So if I make a new file, So here's my new file. This is a file that I just wrote on my host OS. If I re-enter the virtual machine, somebody said amazing. I hope that's not sarcastic, because I do think this is actually amazing. If I go back to my my guest OS, so if this is my guest OS, there is the file that I created on the host. And voila. So this is super useful for allowing you to both do everything on the command line that I need you to do in this class for building, compiling, building, testing, submitting your source code using Git. But then you don't have to be using the command line to actually edit your code. You can use Visual Studio or Eclipse or whatever editor that you want to use, Notepad. Okay, so Control D or exit to leave the session. You see it tells you connection to your local host is closed. So you can tell really easily on the command line whether you're in your guest OS or your host OS. It can be kind of confusing. It's very easy to mistake which one you're on, but just look at this prompt here to tell you. All right, let me show you what it looks like to create this virtual machine. Now, I would suggest trying this now, but it does take a little while. It takes takes a little internet speed to download this stuff. Well, actually, let me show you the next command, which is really useful. If you feel like something went wrong with your virtual machine, Vagrant destroy will blow away that virtual machine. Now, keep in mind, anything that is on that virtual machine that isn't mapped to your host OS will be gone, basically irrecoverable. So I would really recommend storing everything on your host machine and using that mapped folder and treating your virtual machine as just kind of a stateless tool that doesn't store any of your important data. So Vagrant destroy will shut down and basically delete the virtual machine. And now I can show you what it looks like to create the virtual machine. So I've already downloaded the pre-built guest operating system binary. You'll have a long period where you're downloading that. It'll, I don't know how big it is. It might be a couple hundred megabytes or something. It'll download it for a while, and then you'll see all of this stuff go by. So it's setting up the ability for you to use SSH to go in. So while this is happening, let me answer some questions here. I'm not a mod. My favorite is Ubuntu. Ubuntu is great. I actually use it on my laptop because some of the commercial drivers, commercial hardware, Ubuntu packages those drivers. It makes it easier. Arch, anyone? Arch is great. I love their documentation. I started using Mint. I've heard really good things about Mint. I've never used it though. Ooh, Emacs gang. So I'm a huge fan of Emacs. I like doing as much as I can in the command line. Somebody's trying to initiate a classic Emacs versus Vim debate, which I'm not going to even touch. Let's see. Do you know what virtual machine extension you're going to be working with to test our VMs? So I'm not going to test your VMs. It's just honor system, whether you install it. The homework, if you just say yes, I won't know if you're lying, but please don't lie. It violates academic integrity. So this is really just me forcing, making it a, if I make something, so there's this principle in philosophy and psychology that that people weight losses greater than gains, even if it's the same amount. So if I say make it a bonus for you to install it, nobody's going to do it. If I say you're going to lose points if you don't install it, then people will at least pay attention and do it. But it's 1 point. So just install the virtual machine. It's super useful. Somebody actually said they had an internship where they were using Vagrant. So you're almost certainly going to encounter virtualization in some capacity as a professional developer. So somebody said Vagrant destroy is great. Yes, yes. That's what I did to just redo this. So somebody's saying essentially like when we used Eustace. Yeah, exactly. So with Eustace, you're using SSH to connect to a remote machine. With Vagrant, you're using SSH to connect to a guest machine that's running locally on your native hardware. So it's the same idea. Do we need to run Vagrant up more than once? That's a really good question. So Vagrant up boots the machine, boots the guest machine. And once it's booted, it stays running until you either do Vagrant halt, is it? I can't remember, Vagrant halt or Vagrant down, I can't remember. Or whether you log in and shut down the machine, or whether you shut off your machine. So if you shut off your machine, all the software stops, including the guest OS. So you need to run Vagrant up whenever you restart your computer or if you've previously shut down your machine. Somebody said something about PowerShell. Oh yeah, so sorry, I'm using the GNU Linux commands, and I'll go over that next week. I'm gonna go over through probably dozens of commands. You don't have to know all of them, but I just wanna walk through it and have everyone just sort of get some muscle memory started. Yeah, so command shell, I can help you, or other students can help you with using command shell. Should we install Vagrant on the VM? I think, yeah, so I said, never mind. Is the virtual machine just a compiler work? The virtual machine is to compile, test, and submit. So everything except editing, you really need to do on the virtual machine. You need the GNU Linux tools. Unless, I mean, yeah, I think you probably were best using that. There's certainly ways to do this purely in Windows, but it's not super fun. Virtualization is the easiest way to do that. What if you, yeah, don't tell people to say remove -rf star. I don't know if this is somebody intentionally trying to, get people to do that. Don't run that command. That's a very dangerous command to run. You can just use Vagrant destroy if you want to clear out your virtual machine. It does require virtualization hardware. Your laptop may not have it. If we don't have that, talk to me. It does require some space, probably hundreds of megabytes or maybe gigabytes. Okay, so this last step here, the all in green, this was the provisioning step. So all of this, what looks like garbage output, is installing all of the software that we want for the class. Now, if I make a mistake in the provisioning script, or there's some other software I need you to install, instead of having to destroy and recreate your machine, you can rerun provision. So if you run Vagrant provision, this will do everything here. It'll do everything in this provision section. This apt-get is just a tool in the Linux distribution that downloads pre-built software for you. It's a package manager, and it handles all the dependencies between software. So if you run Vagrant provision again, it'll just rerun this little script here. Let's see. So files that are created. So, okay. Oh yeah, okay. The shutdown command is Vagrant halt, thanks. Another way to shut it down is to use the shutdown command in GNU Linux. So you can say shutdown H for halt now. That'll shut it down. Oh, whoa, sorry, sudo. All right, let's not get into this. So sudo allows you to run root system up stuff. Yeah, just use Vagrant halt to shut it down. Okay, differences between, so no special VPN is needed? No, this machine is running on your own local machine. Files that are created on the host machine where the Vagrant files also show up. So only the files that you create in that /Vagrant folder. I'll go over this more next week as well. Not all files in your host machine or guest machine are available. Only those in that one folder. It's basically mapping one folder in the guest OS to one folder in your host OS. By default, Vagrant maps the /Vagrant folder in the guest OS. So actually here it is right here. So this is the default mapping that happens by Vagrant. So it maps the guest OS /Vagrant to the host OS, in my case, /home/paul/ wherever you put your Vagrant file and started Vagrant. Let me get the rest of these questions. Oh, thank you. I'm glad you liked this lecture. So hopefully we can keep up this momentum for the next couple of classes. This actually went, I didn't think I'd take up the entire time, but we did. Let me just answer the rest of the questions. It's usually keep me engaged. Thank you. When do we need to have the VM set up by? In a week. So the assignment is already up on web courses. So anything that's graded, all the assignments will be on web courses. All right, any other questions before I move to office hours? Oh yeah, yeah, sorry. Can you explain how the directories overlap between guest and OS? Let me show you this again. Let's see. Let me see if it's not too confusing to have two windows open here. Class. All right. On my let's do it this way. On my left will be or on your left will be the host OS. So, oh yeah, so somebody asked, will the lab be setting up this up from scratch with us? Yes, the lab will walk you through setting this up. If you have installation issues, if you want to go through the commands. Yeah, I understand the commands are rough. So next class, we're going to go over, I mean, this is going to be crash course on the command line. I don't expect you, like, there's no way you can just remember these from looking at them. But if you follow along, rewatch this lecture, rewatch next time, follow along and just type it by hand, very much like programming. This is the operational side of programming that's easy to take for granted in class. It's a technical skill. So getting muscle memory and just typing things out just by rote will make you just remember these, and you won't have to even think about it as much. So I know I'm probably typing fast, and you can hear this like machine gun typing. I've always been, this is the impatience part. I want things to happen quickly. So being able to have muscle memory and typing fast is useful for that. All right, so for the person who is asking about the mapping, on my left is my host OS. On my right is my guest OS. We can see that by looking at the command line prompts. Vagrant is my guest OS, and whatever your machine prompt is your host OS. This folder here this folder on my host OS is mapped wherever I put the Vagrant file. This folder on my host OS is mapped to this one folder on my guest OS /Vagrant. So as long as I go to that folder, and I'll talk about using these commands in Vagrant next time, but as long as I'm in that folder, the contents of that one folder on the guest OS are mapped to the contents of that one folder on the host OS. They're always mapped. So if you if you want to edit your source code on your host OS, put it all in this folder. And I'll talk about setting up the Git repo next time. But that'll all be accessible from your guest OS. So you'll do your development over here on your host OS, like coding, and then you just keep your host OS keep your guest OS open on the command line, and you'll run all your commands to compile, test, and submit. And I'll go over that over the next couple of weeks. Does that answer your question on the mapping between the two? Yes, the overlapping occurs in the same folder where you have your Vagrant file. And that's the same folder where you're going to call Vagrant up and Vagrant SSH. Yeah, you have to call Vagrant SSH from that folder. The machine is, Vagrant puts a little, Vagrant is aware of which folder you're in and uses that folder to say which machine they're in. Okay, so lecture is officially over at this point. I'm going to finish the rest of these questions, and I'll move over to that gather space. You're free to go there now and start chatting with each other. So we're going to try that out for a little while. You are free to use that. Remember, it's a public space. The same rules about classroom integrity and UCF harassment policy, all that stuff applies. The gather space is where office hours are. Okay, let me finish these questions. I'll show everyone where the gather space is, and we'll move over there. Directories overlap. I think I covered that. The student who asked that, let me know if you still have questions or come to office hours. The lab will be on this. Commands, I know it's gonna be over everyone's head if you've never seen this. We're gonna train muscle memory. This is not about intelligence or cleverness. This is just muscle memory and just knowing these commands. Oh, when you exit from the virtual machine, does it still run? Yes. So it's just like Eustace. When you exit out of Eustace, the machine is still running. So think of it like that. You have almost like a remote machine, but it's running locally. And when you SSH in and exit, that's just a remote connection to it. If you want to shut it down, use shutdown or Vagrant halt. And you can ask in the labs today for more details if you want to see that again. Since labs are on Zoom, are we now allowed to go to different ones? Yeah, you can go to different ones. I mean, it's just going to be this same Zoom lecture. So you just join whichever you feel like. Lots of command line. Yeah, I'll give links to command line cheat sheets. There's tons. There's a really cool tutorial called War Games. that a lot of my students have used. It's a very fun way to learn about the command line. The big thing I got command-wise was Vagrant short. Yeah, don't use remove dash. Like, I'm gonna put this as a comment. This is like danger zone here. Don't do this. That's a dangerous thing. You'll see people online who are trying to, like, you know, troll people, say, hey, if you wanna install this game, run this command on your command line. Don't do that. It's gonna force remove all of your files that are not protected. So the overlap occurs, yeah, okay. All right, so I think that's all the questions for today. Let me show you the gather space again. All of the entry points to the different technologies in this course are available in the web courses main page. So just to go over it one more time, the syllabus is here that has lecture notes and project descriptions. Lecture and lab broadcasts are all going to be via Zoom through this link. Requires a UCF login. Video recordings will be available, I think, through the Zoom sidebar. I haven't tried saving the cloud recording. I'll try it later today. And I think you can just go to Zoom and see the cloud recording, but I'll have to check that later today. Okay, office hours are here on Gather. So if you go here and put in that password, you'll get a little avatar. It's almost like a little video game, but for doing group chat. Here's Piazza, and then the Git signup links. So this Systems Simple C1 is the one in our first assignment. You'll see if you go to the assignments, you'll see our first assignments. Okay, so that's it for the lecture today. Let me stop recording and just pray that Zoom saves it on the cloud. And I will see you all in office hours in 4 minutes. Bye-bye, everybody.